Welcome to part 4 for our lecture video series for Wednesday, March 15th, where we are now going to move away from chemical bonding and compounds in general to discuss chemical reactions. So let's start by reminding ourselves about where we first heard about the concept of a chemical reaction, and that goes all the way back to Dalton's atomic theory. So if you remember, Dalton's atomic theory states that no new atoms are formed in a chemical reaction. Specifically, what Dalton said was that a chemical reaction involved the combination separation or rearrangement of atoms. So if I start with some compounds that contain only hydrogen, oxygen, and nitrogen, then after a chemical reaction has happened, I better wind up with ending materials that only contained hydrogen, nitrogen, and oxygen. So we are going to add a little bit more detail to this definition because it is still something that holds true today. It's just now we are going to add in a little piece that includes what we know about chemical bonding. So let's define a chemical reaction. So by definition, a chemical reaction is some kind of chemical change wherein the atoms in compounds or molecules have their bonds broken and as a result rearrange or separate or combine. And form, as a result, then new bonds to one another. So if I've got something like, I don't know, compound A, B, that is undergoing reaction to just go to A and B components separately, then what we call a chemical reaction is going to be the severing or breaking of the bond that existed between A and B. And now here we have a separation into components A and B. So this is an example of a separation. So chemical reaction, bonds broken, atoms rearranged, new bonds formed. Now, as we would hope, chemical reactions follow the law of constant composition, but I like to think about this as the law of conservation of matter or mass. So as we've seen before, this means that no new atoms are created and no existing atoms destroyed. So for example, if I had 15.0 grams of AB that was then separated into A and B, I better have in total a sum of masses equal to 15.0 grams. So when it comes to chemical reactions following this law of conservation of matter, or law of conservation of mass, this means that there's something that we need to check for every time we're looking at a chemical reaction. So we need to ensure that a chemical reaction is balanced, meaning that we have the same number of atoms of a given type, same number of atoms of a particular element at the start of reaction as we do as the number of atoms of each element at the end of a chemical reaction. So we're going to talk about balancing in more detail later, but this is coming up where we got to be counting atoms of different elements and ensuring that we have the same quantity as we did before reaction as we do after. Now we've seen this before already, but let's be, thorough and specific about how we would write a chemical reaction. So here we have a general reaction notation where X is some starting material, Y is our final material. So over here on the left-hand side, this is what we call the reactants. They are what are to be reacted together, our starting materials. Then we have this reaction arrow here. And this could be read as to yield or to form. And then over here on the right-hand side of the arrow, these are what we call our products. These are our new or our made materials. And indicated in subscripts here are the phases, solid, liquid, gas, or in solution, aqueous, of each of the materials involved, because we can have a change of phase as a result of a chemical reaction. So for example, let's see here. What reaction do I want us to look at? All right, let's look at the decomposition of sodium bicarbonate. So I would write this as such: NaHCO3 solid goes to Na2CO3 solid plus H2O in the gaseous phase and CO2 in the gaseous phase. And this is because Heat is required in order for this to be composed, so this triangle means heat. And if I were to translate this into English, I might say something like, my reactant, sodium bicarbonate, solid, reacts to form, and I'm going to also include that heat's in there. So reacts upon heating. To form, to yield, to make. Solid sodium carbonate. Product. I've also made here gaseous water or water vapor. And lastly, our final product here, carbon dioxide gas. Okay, so I write out what my reactant is, and then I can say reacts to form, yields, makes, creates, produces. To yield, I think, is something that I'll use a little bit more frequently. To form. And then I've indicated my product with their phases, where again, this phase subscript S means solid, subscript L means liquid, subscript G means gaseous, and then subscript AQ, aqueous, which means in solution. So it's a pseudo phase. It's not technically one of our phases, but it does describe kind of where we might find this particular substance in our chemical reaction. All right. So we are going to discuss at length coming up in this class, chemical reactions. We're going to discuss how we can overcome this idea of balancing. We're going to go over the different types of chemical reactions that you might find and the forms that they will take on. And then we're going to look at those different types of chemical reactions under much greater detail, specifically reactions that occur in solution or aqueous reactions. That's going to be a lot of our focus in lab coming up next week in week number 10. And after we have our conversation about chemical reactions, how they occur, how we can quantify them, talk about them, etc., then we're going to move on from chemical reactions into the why of chemical reactions happen. But we're going to be in the land of chemical reactions for a hot minute, so let's get comfy here. Okay, hope we're doing all right. I will see you all tomorrow if campus is no longer closed. Otherwise, I will hear from you on Friday in lecture.